Kai-Uwe, thank you for giving us another lecture. Give it away.
Thanks. So before I put you all to sleep, let's thank the organizers for what they put up. I think that's really magnificent what has been going on during this week. So let's give them a round of applause. Now I hear something. Thanks. Okay, so let me remind you what the space is that we're looking at. We're looking at the quotient of the spine of outer space mod the Torelli group, and we think of the elements as the points in that space as homologically marked graphs. So a homological marking is just you annotate each edge with a label, and the label counts how many times the first petal of the standard rose wraps around that, passes through that edge netwise. So in orientation and against the orientation is supposed to cancel out, and the net total, that's the number you record. You record that for the first generator, you record that for the second generator, and you record that for the third generator. And so for each edge you get that label, and that label is an element of z to the n. So we think of points in our space as graphs with a labeling of this sort. Okay, so let's start with a rose. And the petals of that, I call the rose row, and the petals are labeled by the vectors v1 through vn. And I want to look at the blow up of that rose. So in that blow up, the edges that came from the petals in the rows, they will still carry the labels v1 up to vn. There also might be other labels, we've seen that already, that there also might be other edges that get the same label. So in this blow up, that's a blow up of the rows up here. In this blow up, there are edges that correspond to the petals, say this guy, this guy, this guy, and this guy. So and this edge here on the left is new. However, it carries the same label v1. So and by the way, I only look at those those labels up to sign, because you can always swap the orientation of the edge, and that gets you a sign change in the label. So it's really a question whether the label of an edge agrees with the petal label up to sign. So so that's an element in the blow up. Now keep in mind that the edges that you blow up, say those are these edges that you blew up, the colored edges, the red and the green one, those are the edges you blew up. That's a tree. And the edges that are not labeled plus or minus vi form a forest, because it's just a collection of the blown up tree. And here's a rule. Let's say you don't want those edges. You don't want to see those edges. So there are two ways of thinking about that. One is you forbid blowing up those edges in the first place. So you impose the rule that every edge you blow up shall be labeled by plus or minus a petal label. That's a subspace of the star of the rose. And this subspace is a deformation retract of the whole star of the rose. And how do you get that deformation? Well, if you are not in that subspace, you blew up some edges like this green one, where the label is not plus or minus vi, and the collection of all such edges form a forest. So you can continuously shrink them down until they disappear, and then you land in your allowed subspace where all edge labels are plus or minus vi. So this is the space that you get, the graph that you get from there. And we call those graphs cactus graphs, because what's going on is that just petals are running around other petals that got subdivided in the process of sliding loops around loops around loops around loops, and that can be stacked and stuff like that. So each of those pictures looks like a cactus where bubbles are glued to other bubbles, and it keeps growing. And the nice thing about that subspace, that is a deformation retract of the rows, is that you can work out its dimension, and the dimension of that subspace is n-2. So it's really freaking tiny. So the star of a rose, that's the colored proposition down here, the star of the rose is homotopy equivalent to an n-2 dimensional space. So that's good to know, because we want to prove that the whole space Y is homotopy equivalent to something of smaller dimension. And this is way more than we need. This is much better than we need. Okay, so how do we go about gluing things together? Now, one thing about this subspace is worth mentioning. So in this subspace, you don't see anything in the frontier of the rows. So if you are at a cactus graph and you blow down any forest in that cactus graph in a legal way, so that there are no, it doesn't matter. Just take any forest, blow it down. Where will you end? Where will you come out? Well, you will come out at the rows from where you started, because there are no new labels. So all that you can get are the old labels. And that means you end up at the rows where you started. So this graph doesn't, it consists of fully blown up edges. So you went as far with blowing up as you, in terms of edge length, as you can go. You cannot make the edges any longer, but you are still not half the way to another rows. You are just half the way on a loop that takes you back to the rows where you started. So in this subcomplex, you do not see the relevant part of the star, the part of one star of a rose that intersects the star of another rose. So these subspaces for the roses are really disjoint, pairwise disjoint. And so if we want to look at the gluing pattern, we have to look at higher dimensional spaces. So we did a little bit too much here. Okay, now it says go to page 16. Okay, so we want to understand the gluing pattern of the roses by means of Morse theory. So Morse theory is just used to settle on an ordering of the roses. The idea is you build the space by gluing in the stars of roses one at a time. And we have to start with the rows of the smallest norm, and then we take the next, and then the next, and then the next, and so on and so forth. So now I have to say what the norm of a rose is. Okay, so our graphs are labeled, and the labels come from z to the n. So we start by imposing a norm on z to the n. And the norm of a vector is just, well, you take absolute values for all the entries. You write down the tuple of those absolute values, and you compare them lexicographically. So if you if you have two such tuples, you compare them starting in the front, and as soon as you find the first difference, you ask which one is smaller, and declare that tuple to be smaller. So that's the lexicographic ordering. It's also just the dictionary order, right? The natural numbers, the absolute values of integers are a perfectly fine alphabet. And 0 comes first, and then comes 1, and then comes 2. And these are n-letter words, and you just order them in the way that you would for any dictionary. If you have a matrix where we think of these labels as rows and columns, rows are vertical. So we think of these as rows. You order them, you just take the norms of the rows and put them together as a tuple. And again, you lexicographically order. And here you start with the last and you go to the first, but that's just, that's not really relevant because the petals of a rose are not ordered anyway. So what do we do for a rose? For a rose, you do the following. Each of the petals, so V1 up to our rose is, oops, let's say our rose is here, and it has the labels V1, V2, V3. Then you would build a tuple like that. And now you have to settle on the order of those norms. And what you do is you order them with the smallest first. So you order the norms in ascending order. But I will always call V1 the maximum length, the maximum norm petal. So V1 will be the maximum label that I see in a rose. So, and that's the order of the rows. It's just this tuple of norms. And keep in mind, each of these norms itself is a sequence. It's a tuple of n absolute values, of n natural numbers. And now we can define what the link and what the star is. So the star is already defined, and the link of a rose is the intersection of the star with the stars of all the other roses. So that part of the link from where you can get to another rose by blowing down edges. So in order to get to another rose, what do you have to do? Well, you have to blow up some edges.
Kai-Uwe?
Yeah.
That's not a normal definition of a star, right?
No, that's so totally not a normal definition of a star.
But you, so you want to say this is the same as if you did use the normal definition of a link?
No, I don't want to say that. That's just what we, so this is,
maybe
it's the relevant thing, right? We want to think of the whole space as being obtained from the stars by gluing them together, right? So our stars are the building blocks. What distinguishes our building blocks from the ordinary cells in a CW complex or the simplices in a simplicial complex is that they already carry non-trivial topology, right? They are homotopy equivalent to these cactus spaces. These cactus spaces have non-trivial homotopy groups. We already saw on page 8, let me remind you. So there is this thing that you can go from one vertex in the spine to the same rows by collapsing two different trees. And because the homology markings end up being the same, so there is a this here is a non-trivial cycle. So in the cactus graph, in the cactus space. So it's a non-trivial cycle in the star of a rose. So our stars of roses are also not what you usually think of as stars.
I think I forgot that we're not in simplicial complexes, but in delta complexes.
Oh, we are not even in delta complexes because the deltas are so at least you shouldn't think that our stars are well, maybe we are in a delta complex. In a delta complex, this could happen too, right? Yeah, right. But I will not make a commitment whether this is a delta complex. What is the case is that these stars are complicated, but they come with cell structures, and the way the way you think about this combinatorially is you look at the graphs, and varying the length of the edges always gives you a parametrization of the cells, right? And when your edges get to length 1 or get to length 0, that's where you hit the boundary of a closed cell. And when they hit 0, this is where you have an identification with the boundary of another cell that comes from, well, now you have a degree at least 4 vertex, and you can blow that up in various ways. So that's where the neighboring cells are. So there are cells that you can think of, but the star itself is not made of one cell, and it already carries a complicated and wicked topology. And what this link is, this is not the usual definition of a link. It's not a space of directions at the center of the star, right? That's definitely not how you should think about it. It's more the frontier of the star. It's the part of the star that also belongs to other stars. So it's the part of the star that you have to cross when you want to go from one rose to an adjacent rose. Then you have to blow up something, and some edges have to get all the way blown up to length 1, and then you have to blow down something else. You have to blow down some of your original petals to actually go to a different rose. So and where the stars intersect, that's where you have edges of length 1 from both sides, right? Fully blown up edges from both sides. So that's where the link is at. And if you look at only that part of the star that connects the rows to adjacent neighbors of smaller norm, that's what we call the descending link. So that was a word of caution. Is that clear? I guess asking question doesn't work on Zoom. Okay, so
how long would it take if I asked you to just quickly tell us again what the star is? I mean, I know it's a homotopy equivalent to these cactus graphs, but like it's okay. I don't know if it's. I mean, if you can do it in 1 minute, then great. If you don't, then we'll have to go on.
So the star of the rose that consists of everything that is the blow-ups of row.
Yeah, that already helped. That's great.
Right. So it's really just those things, and that's so. It is the space of those pictures where you can get to row by blowing down a forest. So just a sec. So gamma, the graph gamma is in the star of rho. That's the same as rho can be obtained by blowing down a forest. Okay, so And now let's think about how to identify things in the link and in the descending link. So a blow up lies in the link. If it has a fully blown up edge, you need to fully blow up the edge in order to trade that in order for it to be a petal in a neighbor, to become a petal in a neighbor. So if it has a fully blown up edge, that after blowing down is a witness that you are not back to where you started. So it better not be labeled with plus or minus in a petal label. So in order to go to the link, you have to blow up an edge to full length with a label that is not seen among your petals up to sign. And if one of those edges has a label that is smaller than the highest petal label, then what you can do is, now that you have blown up your graph, you can maybe blow it up further so that V1 is also blown up, and then you can trade labels. You can trade your worst petal label for the label U. Once you see a label that is better than your worst label, you can trade and you can get to a neighbor that is smaller. So those graphs lie in the descending link. They lie in the gateway to an adjacent rows of smaller norm. So, wait, I forgot to put up these pictures. So where are my pictures? You only need the pictures. I want that picture also to be up there. Okay. And that motivates the definition of a descending edge. An edge is descending if its label has smaller norm than the worst label than the worst petal label of your rows. And a blow up is completely descending if all the blown up edges are descending. And now look at that picture in the small board in the middle up here. So I claim that the descending link deformation retracts onto its completely descending link. So recall, in the link, you will see among the blown up edges a descending edge, but there might be edges blown up that are not descending. The edges that are blown up that are not descending are still part of the blown up edges. So those form a tree. So the subcollection of blown up edges that are not descending form a forest. And you can again blow down that forest, and collapsing that forest will end up in the completely descending link. Because there was a descending edge, otherwise you weren't here. And so there is a survivor. You're not blowing up everything, blowing down everything that you blew up. Because among in order to be in the descending link, one of the edges that you blew up is descending. And so in the projection onto the completely descending link, that will survive. That will not be collapsed. So, and now we will understand the homotopy type, the dimension of this completely descending link. That's the idea. And in order to understand the dimension, we will describe that in terms of cells. So let's suppose you have a fully blown up graph, and so that is all edges have length 1, in the completely descending link. Such a graph I can associate to that graph a polysimplicial cell. So it should be a product of simplices. And here's how this works. For each petal label, I get one simplex delta I, and the dimension of that simplex will be described shortly. And all the other edges I put into their own delta star. So what are my simplices, I should say? So my simplices, an n simplex, I realize in this way. It's the n plus 1 tuples of numbers between 0 and 1, and I insist that one number, one coordinate equals 1. So let me convince you that that is a simplex just by drawing a picture. So what is it for n equals 2? So 3-dimensional. So there is, so if I insist that one coordinate is 1, I get, for instance, so this clearly is the cube, but of the surface of the cube, I get, for instance, the square where z equals 1. I get the square where x equals 1. And I get the square where y equals 1. So these three squares form a hexagon. It's not the whole cube. I only look at the surface of the cube, and I only look at these three squares, and they give me a nice little triangle. So what is delta I? That is the delta for all edges with label plus or minus vi. So those. So
can you copy the last slide to the side?
Oh yes, thank you. Yes, I can do that. So delta I has so what that means is I blow up my edges. One of these edges with label plus or minus vi will be the original petal, but there might be other parallel edges that carry the same label, and of course, in blowing down, I can just choose any of them. Now, what do I want to say? In order to be in the link, I need to have fully blown up things, but only one of them needs to be fully blown up. And similarly, the other edges, the remaining edges not labeled. So that parameterizes a cell, and one can work out the dimension of the cell, the dimension of that C gamma, which is this is equal, oops. Is equal to the number of vertices in gamma minus 2. So in particular, C gamma has top dimension if and only if gamma is trivalent, and then one can work out what that is. So how many vertices do we get? So it's 2n minus 2, the number of vertices. And if I have to subtract 2 more, then I get that the dimension of C gamma is indeed 2n minus 4, which is 1 too many. So we want to get rid of one dimension, right? That's
2n minus 3, and we want to show then that it's that.
No.
So I mean, you just said that it's. Wait, what did you say about the dimension of C gamma? Didn't you just say it's 2n minus 3? Oh, I'm sorry. What?
The dimension of C gamma is a cell in the link. The link has codimension 1 compared to the whole space.
Yes.
The whole space has dimension 2n minus 3, and we want to get rid of 1.
Yes.
In order to do that, we already reduced the stars of roses to up to homotopy equivalence, n minus 2 dimensional stuff. Now we're working on the intersections of roses, right? And the descending part of that connects a rose to what is already there. And that is a priori 2n minus 4 dimensional. It has codimension 1 in the 2n minus 3 dimensional space. And we want to get rid of one dimension. So also in the descending links, we want to get rid of one dimension. We want to bring this number 2n minus 4 down to 2n minus 5.
Okay.
Right. This is a number. This equation is in the link. And that's important. That's why we lost one dimension already just by looking at the link. Okay. So and here's really the key. Oops. Let me not show you that to you yet. Here's the key lemma. Namely, if you have in the blow up an edge with this label, so it has a V1 component. Keep in mind, V1 is the worst petal. That's the longest, that's the petal label with the largest norm. And let's suppose you see one of the edge labels in the blow up. That is a linear combination of the original petals, and assume that the petal 1 got split, so it contributes to the edge label of this blown up edge. And the others may contribute according to whether they were split or not, and if they were split, according to their orientation. So these coefficients are -1, 0, or 1. 0 for those that are not split by this blow up, and -1 if you chose the other orientation, if they are split opposite to the way that the first petal was split. And assume that this guy here, this label, is descending. So its norm is less than the norm of V1. So this is descending. Then I claim if you change the signs for all the others, you keep the sign of V1, but you change all the other signs. That's what we call the opposite label. I claim this guy cannot be descending. And the reason is just this observation about integers that, so how does this work? Keep in mind each of these labels.
Kai-Uwe,
Yeah.
We sort of still back 2 slides. We're 2 slides behind you. So, sorry.
What do you mean by you are 2 slides behind me?
Yeah, there.
You're there. Yes.
No, just by mentally.
Okay.
Thanks. You know, I mean, you define this C gamma. So we're looking at this descending link, right?
Yeah.
And then you take a graph there, and then you define a cell. But you haven't really told us, you know, so now I should think of this cell as inside the link.
Yeah.
I mean, you're sort of covering, you're saying that these cells are sort of covering.
Oh, I see. Okay. How do they parameterize points in the link?
Yeah, where did that funky this definition of the simplex come in, for example?
Right. Okay. So indeed, you're just 1 slide behind, I guess. So the point here is,
Great.
That's good.
So the point here is that the delta I comes from, let's draw a picture. You're absolutely right. This has to be done by means of a picture, I guess. So let's see if I can whip up a picture. I should. So let's say we have V1 here. We have V2 here, V2 here. Now, of course, I'm V2 plus V3 here and V3 here. Right? That's a perfectly valid picture, and it could be completely descending if this label is descending. So let's assume that V2 plus V3 is actually less than V1. So what is the corresponding cell? So this is gamma. So what can we do and stay in the link? In order to stay in the link, we always have to have we have to have fully blown up edges for the petals of the other rows that we could go to. So any rows that we could go to needs to have fully blown up petals. So this has to stay at length 1. This has to stay at length 1. This has to stay at length 1 because we need to be able to go to 2 different rows, right? Depending on whether we blow down V3 or whether we blow down the sum, we go to 1 rows or to another. But these guys here, these 2 V2 guys, only one of them has to stay at length 1 and the other one can vary. And if I have both of them at length 1, I can swap and make the other one shorter. So this is delta 2, which is an interval. But this interval you should think of really as sort of the corner of a square. Probably I should draw that like this. So one coordinate being 1. So, and let's make that color coded. So we have the red guy and we have the green guy, right? And so we have the green guy being length 1 and we have the red guy being length 1. So a point on that, in that delta 2 thingy, like this point here, that corresponds to, well, the red edge has length 1, but the green edge has length 1/2, and the other edges are still there, right? So are still at length 1. And this way, you also see that if you make this really, really short, like if this tends to 0, if this goes all the way down to the rows where you have this, well, not a rows, a theta graph. right? Then you get a different combinatorial type, and that corresponds precisely to this endpoint, right? So that's why there really is the boundary of the cell. You already hit the boundary of the cell. So this is how these cells parameterize points in the link, just by means of, and if you have multiple labels if you have multiple edges that are all labeled V1, you get the same thing for, you can trade length between these edges. And if you have multiple labels that are not labeled V1 up to Vn, all of it doesn't matter which of these labels is fully blown up. You can shift the length between them. As long as one of them is fully blown up, you can always blow down to an adjacent rows, because that one label that is not V1 up to Vn is all you need to get to a rows that is really not the rows you started from. So that's why the delta star collects all the other edge labels.
That's exactly what we were missing. Thanks.
Okay. So I like pictures. Oops, now I have a picture somewhere. Let's see. So okay. Opposite labels cannot be both descending. Yeah, right. So why? So keep in mind these labels, let's say V1, that's just some numbers, right? That's A11 up to A1n, and in fact they're absolute values. So if you modify that by adding in a linear combination of other labels, then what happens? Well, you replace these numbers by, well, you add or subtract stuff. And so now what happens if you compare the absolute value of a number that you changed by some other number to the absolute value of the number itself? Now, I claim one way of not changing the label, the absolute value, is of course, no, I don't want to claim an equivalence. So one way to actually not change anything is that b equals 0. So the way I think about this is as follows. So I have my number a and I have 0, and then I move a by plus or minus b, right? So, well, wait, plus b and minus b. I'm thinking positive numbers, obviously. But anyway, so so if adding b gets me to 0, I'm not thinking positive numbers. Doesn't really matter. Signs won't matter. So the point is, if this sum is closer to 0, the difference will not be. Right? So if I go to the other side, then I clearly depart from 0. So if b is non-zero, then I will either move towards 0 or I will move away from 0. If I move away from 0, the absolute value is bound to increase. If I move towards 0, the absolute value might get smaller. But then, of course, I might also overshoot and end up way here. And then it's bad again. But that doesn't matter, because by assumption, I'm only interested in the case that I got closer to 0, or at least not departed too much. So the only way to get closer to 0 is to actually get away from 0 if you change the sign. And that is the reason why if this label is descending, this label, the opposite label, cannot be descending. That is the key observation about this Morse function as far as counting dimensions is concerned. So where, let's put that here. And now we can already see where free faces come from. So here's an example of a fully blown up graph, so of a trivalent graph. So the gamma that comes from this graph, the C gamma, has top dimension. This indexes a top dimensional cell. And I claim that, so again, I have V1 is max, right? And I claim that this guy here has a free face. This cell has a free face that I could push in. So what are faces? Faces of C gamma. What happened here? That didn't look too good. So the faces of C gamma are given by shrinking edges down to 0. So by collapsing an edge, I get to a codimension 1 face, right? Collapsing one edge, just identifying 2 vertices, that shrinks the dimension by 1. So a codimension 1 face is obtained, and I claim I can do that by just looking at the top label, the worst label, and collapse this edge here. So why does this label here, this face here, why is that a free face? Well, this vertex can be blown up in 3 different ways, right? So there is the blow up like that. There is the blow up like that, and there is the blow up like that. So let's look at the blow up where you blow this vertex up horizontally. Let's look at that first. This here is not a valid picture in the space because this blow up has a separating edge, and we do not allow that, right? We are working in reduced outer space. So this separating edge tells me that this cell really isn't there to begin with. Whatever this graph wants to index, it won't be a cell in the completely descending link. This is not an allowed picture. So along this blow up, I do not see an adjacent cell. Similarly, what is this blow up? This blow up is where I changed the order of the edges, the order of the way these 2 horizontal edges are attached. Or another way of thinking about this, I changed the orientation of this edge. So in consequence, the label of this edge has changed. Here, I was adding V2 and V3 to V1. And now, since the orientation is reversed, the orientation of V1, I subtract them. And this is where the key lemma kicks in, right? So the key lemma says that if this label up here is descending, then this label down here is not descending. So even though this picture is a perfectly fine picture and it parameterizes something, but it's not parameterizing a cell in the completely descending link because the edge label is not descending. So that is why of the 3 blow-ups of this graph, only 1 parameterizes a cell in the completely descending link, And this cell therefore has a free face indexed by this graph. So this is how you identify free faces, how you see free faces. And you can push them in. And the claim is, if you keep pushing, if you can keep collapsing top dimensional cells away by just pushing in free faces, you end up at something that has no 2n minus 4 dimensional cells anymore. The claim is you get rid of all of them. And that works as follows. So let L be the complex that I just talked about. You start with a completely descending link, and you push in free faces until you don't find a free face to push in anymore. So the claim is that this complex L, by the way, that may depend on the order in which you pushed in faces. This complex L does not contain any top dimensional cell. So a 2n minus 4 dimensional cell, or equivalently, and that's what we're going to use, a cell indexed by a graph gamma, by a blow-up, where all the vertices are trivalent. Okay, so assume not. Assume my complex L contains still top dimensional cells. Okay, among those, I consider a graph gamma such that the V1 loop in gamma has minimal length. So keep in mind there's this cycle that corresponds to the you blow up a petal that is labeled V1, right? So this petal, you blow up a tree and the petal is attached to possibly 2 points in that tree, and the line that joins these 2 endpoints of that first petal, that is the V1 loop. And you want to choose your gamma so that this loop has minimum length. So the first observation is that that the V1 loop cannot be a single petal by itself. And the reason is that our gamma is trivalent. So this vertex where your V1 loop is attached to the rest of the graph, that would be a trivalent vertex. And that means that you have a separating edge connecting your V1 loop to the rest of the graph. And there are no separating edges. So the V1 loop clearly has to have length at least 2. And this is the central picture. So let's assume we have, so this is the graph gamma. The cell that it parametrizes is in our complex L by assumption. And I'm not shooting for the free face right away, but I want to understand what the neighborhood of this cell looks like. So since the V1 loop, what is the V1 loop? The V1 loop is this guy here. That's the V1 loop, right? And I look at 2 edges that are hanging off the V1 loop. And I look at the face of this cell that corresponds to collapsing the edge in between. So that's this guy. And again, this picture can be blown up in 3 different ways. One of them gets me where I came from. One of them gets me to the horizontal blow up, now the vertical blow up. So I blew up this edge that actually takes these two edges and separates them from the V1 loop. Now, this picture here is not in L. And the reason is that I chose my gamma with a minimum length V1 loop. And in this picture, the V1 loop would be shorter. So this is not an L. This just isn't. So the only possible picture in L is this guy, where I start from the middle and blow up in the different orders. So these two edges now swapped sides, right? What was previously on the left now is the right edge, and what was on the right is now the left edge. And this has to be a neighbor in L, because otherwise this guy here would have a free face, because this neighbor isn't there. And if this neighbor also wasn't there, then this would be a free face of this. So since L has no free faces that I can push in anymore, that means that if I see something like this, I will also see the same picture with the reversed, with the swap of the two adjacent edges. So that's a fundamental observation. I can swap the order of two adjacent edges and move about in my complex L. And now finally, we can see how the key lemma enters this argument. So I can use these swaps of adjacent edges to build a gallery from one cell to the next cell, to the next cell, to the next cell. And what I do is I use a lot of neighbor transpositions, like n choose 2, something, or L choose 2 for the length of for the V1 loop, so that I swap the order of the feet completely. So if I have my edges, my incoming edges labeled E1 up to E4, after the transformation, I have them in the order E4 up to E1. And I know that along the way, I always look at cells, top dimensional cells in L. They all have to be there. Okay, but now I claim there's a contradiction, because if I look at the labels, this is again a matter of orientation, right? So on this edge here, on this particular edge, I see the label V1 coming in, and then there is something that is contributed by E1, and some of it may just fall off from E2. So what goes from E1 to E2 and to E3 and to E4. So what comes from E1 is all here, and it gets added to, so this is effectively the label of E1, right? So I guess and here on the opposite side, I see that now my label is V1 minus whatever was contributed by E1. And since we are in the completely descending link, I know this is an edge label that is descending. And since this is also supposed to be in the completely descending link, I know that this is an edge label that is supposed to be descending. But the key lemma says they cannot both be complete, they cannot both be descending edge labels. So there is your contradiction. So that's why it doesn't work. Whoa. And I guess, so the remainder of the write-up is how you actually use this in a little transfinite induction to deduce that the overall space can be realized as a 2n minus 4-dimensional complex. So let me just be very brief on that one. Let's see, first of all, now this is really all that there is to it. So we have seen that the descending links can be homotoped so that they are 2n-5 dimensional. The roses themselves are n-2 dimensional. And now it is very tempting to say that, well, therefore, the limit is 2n-4 dimensional. But that there's a subtlety, right? We have seen this iterated mapping cone construction where you have like circles and maps between those circles. So this is times 2, this is times 3, this is times 4. So this is degree n maps and so on and so forth, and it keeps going. And the mapping telescope of this thing is not homotopy equivalent to something one-dimensional. But at every finite step, if you cut off like at a finite stage, the whole mapping thing collapses and it's just homotopy equivalent to a circle. So what I'm saying here is you have to be a little bit careful on how you want to run an argument that that goes for the dimension. And what you do is not only do you have to, well, you actually have to construct a 2n-4 dimensional complex along the way, and also homotopy equivalences of the finite stages, so that in the limit you get a homotopy equivalence. So that will be in the notes. And I stop here. And I don't hear anything.
Can you you did not hear us?
Well,
You didn't hear us clap?
I didn't hear you clap.
Well, clap again.
Oh, thank you. Thank you very much.
Did you hear this clap? Yeah, thank you, Kai-Uwe. Let me first ask. Let me first ask Zoom. Is there any question from Zoom? If there's a question here, maybe you can already come forward. All right, we have a question here from Andrea.
So you show that this yn is 2n-4 dimensional, at least up to homotopy. I mean, this is the main result, right?
Yes.
And and this is different from the 2n-3 dimensional complex, which is which is the quotient of the outer space by, not by the Torelli, but by the entire out of n, right?
Also by the Torelli subgroup. It's just the dimension of the spine.
Yes, but I mean, up to the homotopy dimension of the quotient of the spline by the entire out Fn would be 2n-3, right?
Oh yeah, yeah.
So basically, quotient in less makes the homotopy dimension 1 unit less.
Yes.
If you don't quotient at all, you get something contractible, so dimension 0. In some sense, there is this. I mean, there is this pattern that the less you quotient, the less your homotopy dimension will be. And let me now come to my question. So suppose that you do something in between Torelli and the entire out. for instance, you consider graphs which have what did I have in mind? Don't have a homology marking, have something a little less than it.
No, I think you want to go in the other direction, right? You want to
So
you want to take like you want to go from the out of N to the Torelli, and then lower subgroups of the Torelli group. And
okay, so Peter will ask then a question later about this. So my question, the example I had in mind was the following: you have so consider the moduli space of metric graphs of rank n, and they are only endowed with one homology class. Say you don't have a basis of the homology; you just have the first element of the basis.
What's the question?
The question is now: can this argument work also in this case, and get to the, what do you think? I mean, probably it's difficult to answer this question immediately on the spot, but you guess that this would be already to n-4 dimension up to homotopy, or still to n-3, if this makes sense. And then Peter, I guess, wanted to ask about smaller subgroups. So maybe you want to mark your
I mean, there are these subgroups like K, like there are some subgroups that he knows about that you could go further down.
Right, like in the Johnson filtration or stuff.
Yeah,
like
for example, yeah, in the Johnson.
So about neither question I have thought. So this is just wild speculation.
Open problem for the we'll put it on the
yeah problem. Well, of course it's an open problem, but I have to sort out my gut feelings here, right? So what should I expect to be true is of course still interesting, at least to me. And I would expect that you have to be very close to Torelli in order to actually go down to dimension 2n-4. And with respect to the others, with respect to the smaller subgroups, I wouldn't be surprised if that actually makes the complex smaller dimensional. So in the Johnson filtration, I would expect to see smaller cohomological dimension.
But you have to stop at some point, because you can go infinitely down in the Johnson filtration, but you can't go infinitely down from -4.
Negative dimension.
So maybe that's like there should be one place where it stops. Yeah.
Right. But
is it clear that all the Johnson kernels have at most the dimension 2n-4 even? I mean, it doesn't, not even that is clear, right?
Well, I mean, cohomological dimension, there's a bound from subgroups to the ambient group, right?
Okay, that's what I was asking.
So
you get a call, don't
you? Sure.
So I do remember that in the mapping class group case, the higher order Torellis, there we actually wrote down a conjecture to the extent that the dimensions go down. So there is something, but we never thought about that in the context of out of n.
Okay, thank you. Do you have another question, Andrea? Is there another question on Zoom? I have another question. It's slightly unrelated, but still very related. Do you know anything whether IAN is a duality group?
Oh.
I mean,
No, no.
Do you have, I mean,
Do
is
I
there
have
a reason why it couldn't be? Is like the dimension difference 2 out of n, does that
well,
tell you immediately that it can't be or something?
well, the dimension is different to the dimension from out of n, but that doesn't mean anything because it's not finite index, right? So,
I mean, if it was finite index, it's automatically a duality group.
right. So,
Okay. Another problem for the problem set. All right. Are there any more questions? Natalie, you had a bunch of questions. No. All right. Let's thank Kai-Uwe again. And I'm sure together with Jeremy and Natalie and Jesper, I'm really happy how well all of the talks were prepared and executed and presented. And I learned a lot from this. So I'm really happy how you guys all fit your stuff together, what you prepared. And I would like to thank you guys again, all of you. I mean, I know that's only Kai-Uwe here. No, it's like there's some in the audience as well, like how everything worked together. So thank you again.